Okay, good morning to all of you. So, today we are going to discuss this formation of complex. So, and basically the thermodynamic aspect of that. And as you know, I told you when you go to the lab, you have prepared complexes. Every time you have made a solution in water. Okay, so in laboratory frame, you have to realize that everything starts with making a solution in water, and as soon as the metal ion is dissolved in water, it is surrounded by solvent molecules which behaves as a ligand. So you have aqua complex at the beginning, at the very start. मतलब आपको शुरुआत में हमेशा ये एक वाटर के साथ मेटल का कॉम्प्लेक्स है, यही रहता है। और जो नया जो भी लिगेंड आएगा वो वाटर को रिप्लेस करेगा. So any new ligand that you are introducing into the solution will replace that thing. Okay, and so it has to be visualized as a ligand substitution reactions. Water will be replaced. Water is the solvent which also acts as a ligand. So water acts as ligand, and if the new ligand that you have introduced into the solution makes a stronger bond, well, it will be the new it will be replacing the water in that complex. But if it is not strong enough, it may not replace. So that is how we visualize one by one. You start with like say M, you have H2O6. So this is your starting point, and then you have some complex additional ligand mx, which you can write as, so each of the steps is to be indicated as equilibrium, like this. So this water molecule will be replaced like this. So this is you have to write with that. So okay. So the thing that I was telling you, that so it is gradually, step by step, it is the reactions. uh, Initially you have the moment metal is introduced in this thing. So Mn, so suppose you are starting with Mn metal ion. uh, it is surrounded by water molecules, so and it forms a octahedral complex, and then each of these water molecules will be replaced and a new complex is gradually formed. So sorry, this has to be, discard this. Okay, so this is what I was telling you, that everything has to be visualized in a stepwise manner as a replacement of water from the NH2O6 complex. So like that, you have to see it like H2O. So this is how you have to visualize the complex. So this is the situation, and now when you have X minus ion, this will replace one of this from okay. सो ये इस तरह से आपको देखना है कि एक कोई लिगेंड यहाँ पे रिप्लेस हो जाएगा. सो सपोज वी रिप्लेस दिस विथ X, rest of it remains as it is. Okay. So things like this will happen, and one water molecule is in the next step. Again you will write, so X minus, which was here in water, the same solution, is now replacing the water H2O as a ligand in that. So this will happen only if X minus forms a stronger bond. Then this reaction will go in forward direction, and more this complex is formed. So in a similar fashion, the next step you can have MH2O 5X minus plus, again you can, another X minus can come. So in this manner you can go on writing. So another H2O will be replaced. So this is what we mean by ligand substitution reaction. Every formation of a new complex in water molecule is a ligand substitution reaction, because the water molecule, as soon as it is dissolved in water, any transition metal ion, it forms, the water molecule surrounds them, and then it forms a coordinate bond like the one that I have shown here. And so you have this kind of, in a stepwise manner you can go on indicating. Suppose we have not yet indicated the charge here, n plus x minus, so here it will be n minus 1 and so on. And so on. So you can think of in this manner. You can have, finally there will be a stage at the last point you will have one water molecule left. So in this manner you can visualize, sorry, not 5. So finally this is the situation that will come when the last, in the last step we show that the last, so at every step, so there will be such steps, each one indicating having a formation of a new bond with mx, and water molecules are being released from that. So in this manner finally you will achieve mh2o, sorry, mx6, so ligand n minus 6, something like this would be there. Okay, so this is how we have to visualize the things. So just like this. So okay, so like this you will have the formation of complex will result, and mx6 complex is formed. So it is not necessary that every time you have mx6 all the 6 ligands are replaced. No, the first experiment that you did in lab, what was that? Iron thiocyanate, and you have got that example. In that case what was happening in that is, so you have just, so it is not, as I'm telling you, uh, it is not necessary that all the water molecules 6 out of 6 will be replaced. It all depends on the thermodynamics of the system, how the how strong the new bonds are being, new bonds are they stronger than the water molecules, metal water, uh, water bonds. So all those things have to be seen, and then only you can describe, write these things. So for example, when you have done this experiment in the lab, thiocyanate, FeH2O6, and you try to find the formula that how many thiocyanate ligand can combine with the iron, Fe3. So what did you got? What did you get in the experiment? You have जॉब्स मेथड आपने किया है, आपने देखा जो आपको मैंने कहा था कि ऑब्जर्व द मैक्सिमम पीक वेयर यू आर गेटिंग, you will be getting the maximum peak at when the mole fraction is of SCS minus is 0.5. So that gives you that the complex formed is having 1 is to 1 ratio for metal is to ligand. That is, the formula is ml, not ml6, right? Ml. Rest of the, so when we started with the water molecule, there were 6 water molecules associated with the metal, and when the amount of metal and ligand are appropriate, the maximum amount of complex is formed and you get maximum absorbance. So it is only one SCN which replaces the water molecule. The rest of the steps is not done. So this is what you naturally get. So each of the ligands have different capability, and accordingly they replace the water molecule to a differing extent. And these are the things that we are going to discuss. So the formation, suppose if it, but in case of when you made ammonia complex, cobalt amine complex, all the 6 water molecules were replaced. In case of ammonia, all the 6 water molecules were replaced by ammonia when you added the ammonia complex to cobalt solution. But here when you take FeH2O6 and then add SCN minus, you find that only one of the water is replaced, no matter how much thiocyanate you add, only one of the water is replaced. So this is something related with the strength of the bonds. The new ligand must form stronger bonds. If it is not, then the replacement, it will be a weaker complex, and uh, it may not go up to the replacement of all the 6 water ligands. So this kind of, so each of the steps are written as an equilibrium, which is reversible thing, you see here. And the Kf formation constant can be written product by the reactant, so concentration of both the terms, that is Kf. And this, it represents, the Kf represents the strength of binding of ligand in comparison to water. So if they are stronger than water, then this Kf will be uh, positive and high magnitude. So this is what we expect if the binding is stronger. And so in this case, if they are weaker, if they binds, the binding with the new incoming ligand is weaker, then you can expect that Kf2 will be, can be negative, it can be very very small value. So the kind of binding that we can visualize is like this: thiocyanate, only one is replaced, and Kf we have just discussed. Equilibrium constant in general, you write step by step for all of them: K1, K2, K3, and up to Kn and n minus 1 L. So this is how in general we can write mln by just one ligand less in the denominator, n minus 1 into L, the concentration. So these, each of these steps that we have written for replacement of one water molecule at in one step, that is called stepwise formation constant. And to calculate the overall formation constant, which is represented by beta n, we have to consider the final number of ligand that binds with the metal. It is actually replacing the water molecules as ligand. and what is this thing, okay. And so this beta n, if it can be shown experimentally, if you write all the stepwise constant, formation constant, which is very easy, you can easily verify that the final overall formation constant beta is just a simple multiplication of k1 k2 k3 up to kn. So for example, you can have an example of cadmium amine complex, and here you have cadmium plus ammonia. So everything is happening in water. So many times people do not write water molecules in the bracket, but it should be written. So you have to assume that yes, it is the water molecule that is being replaced in each step. And then, so there's a thing that you can observe. The first k1 10 to the power 2.65, k2 2.1, k3 1.44. So the power is decreasing. So the value in the stepwise dissociation constant has a general trend that the k value is usually less and less for each consecutive steps. Okay, each successive steps will have smaller k value. The equilibrium constant will decrease. So summation of these, if I try to find the whole overall formation constant, we have to take the k1 k2 3 and multiply it with each other. So the power terms all get summed up and you get this value. Okay, so that's how it is calculated in a very simple way. And so so previous example FeSCN, only one molecule, water molecule was replaced, but now we are going to discuss example of nickel water complex, uh, hexa aqua nickel, which in which all the six. So this is the overall reaction, where you can write this is the overall reaction showing the replacement of 6 water molecules with the 6 ammonia ligands, and the 6 water molecules are released from this. Okay, so there are 6 steps leading to the formation, and we can each step you have you can write like the simple one: metal plus ligand Ml, formation first, second Ml plus L, then F2 K F1 K F2. This is how we denote F1 first step, F2 second formation constant, and these are stepwise formation constants. And we can find this for any particular step. You can easily, so Kf, the formation of it can have a wide range. So we can see here with ammonia, if you want to see magnesium 1.7, very small value of Kf, calcium very small. But if you look at copper amine complex Cu2 plus 2 into 10 to the power minus 4 Cu plus 10 to the power 5. So what does that indicate? So इसका मतलब क्या हुआ कि जब इक्विलिब्रियम अचीव करेगा, इक्विलिब्रियम पे जो प्रोडक्ट का कॉन्सेंट्रेट 10 to the power 5 times larger than the reactant. So if this is larger, so suppose if this is 10 to the power 5. For example, let's take the example of copper here. So if you have this thing as the starting point, you are writing Kf is equal to 10 to the power 5. That means Cu plus, okay, and plus N is 3. This is giving you, so MLN. So when the product that is being formed is having concentration which is very high, 10 to the power 5 times higher than the reactant. So अगर ये 1.7 है, मतलब at the equilibrium the product is one having concentration 1.7 times higher than the concentration of Mg and NH3 combined. So very small, but if you are taking here, it is 10 to the power 5 times factor, so most of it has been converted into products. So higher the value, that means the products are much higher in number, and you can all consider that the binding between metal and ligand is stronger. Okay. So this is important. The stepwise formation constant tells you about relationship between the structure and reactivity. Besides the strength of the bonds, they also tell you about the structure and reactivity uh, with respect to water as a ligand, and then compared with the new ligand that is coming in. So so we have just discussed how we can relate the two things for overall formation constant. And if you compare so this is an example where we are comparing the first step, ammonia is getting combined with the this NiH2O6, starting with NiH2O6 plus NH3 as ligand, which gives you, so all the 6 water molecules are going to be replaced in a stepwise manner. Okay, so like this, so with charge on it, so indicate the charge is 205 NH3 2 plus water molecule, like that. So in second step, so you write in your copies all the steps for 1 2. So second step you will have, for the second step you will write NiH2O 5 NH3 okay plus NH3. So in this manner you should write all the steps in your copies in your notebook. Okay, so by now you should understand that when we are writing H2O, so in each step and so on, so you can continue till this all the water molecules have been replaced. And this kind of situation is what so if we compare this each of the formation constant, step 1 step 2 step 3 until the sixth, so the Kf values 525 148 45.7, so it gradually decreases. This is a general trend, decreases. Kf decreases with replacement of each of these water molecules until you have all the NiNH3 H2O NH3 5. So this is in the last step, so this is your final step where NiNH3 6. So in the last step, all the last water molecule is also replaced, and NiNH3 6 complex is formed, hexaamine complex. Now look at the values of this thing. Each stepwise constant, the first stepwise constant is having the largest value, then it decreases and it goes on decreasing and decreasing till 1.1. So 525 to 1.1, that's the order. So you can take the log and it will appear as the power to the 10 Okay, so this is how you obtain. Now, very interesting thing that you will observe here. Take the ratio of two successive formation constant. मतलब K2 by K1. So this is K2 by K1. This is what? K3 by K2. This is what? So every successive, take the ratio of every successive formation constant, and you will see an interesting pattern here. So बहुत इंटरेस्टिंग पैटर्न एक आप देख रहे हैं यहाँ पे 0.28 0.3 0.29 सो लगभग 0.3 के आसपास सारी वैल्यूज हैं in the entire situation we find that for every successive experimentally it has been found that each one of them is when we compare two successive equilibrium constants formation constants here uh, then the ratio is almost constant 0.28 0.3 so all around 0.3 0.3 is the value that we find here for such. So this is how in general when all the in octahedral pattern if the things is replaced and things like this will happen. Okay, so this is a typical pattern that we observe, and sometimes there is deviation from this particular trend, and that signifies something there has happening in with respect to the change in structure or uh, the spin a number of unpaired spins that is there present in the model. So this was the case assuming there is no change in the spin multiplicity, there is no change in the structure of the complex. In that case this kind of trend is observed in majority of the cases, but in some cases you will find that this trend undergoes the deviation, suddenly deviation. So 1 2 3 you expect it to decrease, but we'll see one example over here that reversal of this trend of f into fn minus is usually an indication of a major change in the electronic structure. That is the talking about this electronic structure means spin orientations and or the geometry electronic or the geometry of the molecule is changing. So something anything like this can happen. In that case there will be a strong variation in the it will not follow the trend. General trend is that f1 f2 gradually decreases kf1 kf2, but if something like unusual happens the trend may not be followed. So that exception kind of thing that happen here is discussed. So taking example of bipyridine as a ligand, when we it is reacted with Fe2 in water. So this is your Fe2 complex. Bipyridine is the complex ligand, and then you start with gradual replacement. So it is a bidentate ligand. It is uh, so bidentate. It is bidentate ligand. So in a octahedral geometry, you expect to so 6 water molecules will be replaced by 3 bipyridine in the final situation. So let's see what happens here. So when you form so what is so the configuration here is that you can see here first step kf1 is 4.2, second step kf2 it is decreasing 3.7, but finally see the trend. First with second, okay, fine, F2 has decreased, but F3 has increased. Abrupt. So what we see here is an abrupt increase in KF3. The value of KF3 is suddenly increasing, which is surprising, which is not following the trend. So here, how do we explain that? So here it is. So initially, in case of water, it is a high spin complex, and then bipyridine binds. One bipyridine binds. There are still four water molecules associated with it. Another bipyridine comes in the second step. So two pyridine binds, and finally in the third step, when it is the third bipyridine comes in and binds to this complex, the this this was in this case there is change in the electronic structure, that is from a high spin to low spin. This is a low spin complex, and here till now it was started with a high spin, and suddenly when finally it is, so transition from high spin to low spin, when it happens you get unusual stability in the system. Okay, and also because bipyridyl is a, it has two donor ligands, so it will be forming a complex. So it is kind of ring will be formed. So mainly, so observation is in contrast to the general trend observed in this case, in the formation or replacement of water as ligands with, in case of ammonia or other things. So here it is to be noted that there is a change from the T2G EG configuration undergoes a change in this complex, and you have from a low spin, high spin to low spin structure. So it is a D6 system, and you have very stable low spin complex is formed. The stabilization increases, and due to the increased LFSC, the formation constant undergoes sudden increase, abrupt increase the Kf value. So it is forming, stabilizing the whole system because of this factor. Similarly, we also find the deviation from the trend when we analyze the complexes of halogen complexes of mercury with halogens. Particularly example here is given with chlorine. So starting with mercury aqua complex Cl minus, one replacement Cl5 H2. So here 6.74, 6.48, but the third one is surprisingly very low. So you can see usually in normal case kf2 by kf1 follows the order of what we have seen, zero point 0.3. This is what is the normal situation. Normal situation is that when you compare k2 k1 k3 k2, any successive rate constant, it will come out to be around 0.3. It will decrease, but it will not decrease in that abrupt manner. So when we are discussing here, we can see that although it is an overall decreasing trend, but the decrease between f2 and kf2 and kf3 is a sudden decrease, very sharp decline. So decrease in second and third value is too large to be explained by the simple uh, uh, reason, statistical interpretations. So this, what does this indicate? This indicates that 1, 2 and 3, when you have in the second, between second and third Cl HgCl2 6 and this 4 H2O, here when three HgCl ligands are coming when the third Cl minus binds in, the geometry of the molecule changes. The geometry of the complex changes from an octahedral to a tetrahedral structure, and that's why the stability formation constant undergoes a sharp change. ओके, सो एनी सच ट्रेंड, जब भी आपको ऐसा कुछ एग्जांपल मिले जिसमें कि सक्सेसिव फॉर्मेशन कांस्टेंट का वैल्यू अब्रप्टली इंक्रीज कर जा रहा हो, या बहुत ही मेजर चेंज आ रहा हो, डिक्रीज दिख रहा है जैसे यहाँ पे, जरूर इसमें कुछ ज्योमेट्रिकल या इलेक्ट्रॉनिक स्ट्रक्चर में चेंज है. सो यहाँ पर हम देख रहे हैं कि ये जो सडन डिक्रीज, एब्रप्ट डिक्रीज, बहुत 6.48 लॉग के इसका 0.95 जो आया, इसका रीज़न ये था कि इसमें जब जैसे ही तीसरा थर्ड Cl माइनस आता है, there is a change, and the change in the geometry happens. You have also, you can see, 3 water molecules are released, and it adopts a tetrahedral geometry. So this is the tetrahedral geometry that we are seeing here, which was, so initially starting from an octahedron, we are having something like this. So change in the geometrical, so a change in 6 coordination system to 4 coordination system, so that leads to with a decrease in the formation constant, that is the less stable complex is formed. Formation constant can also be related to this unusual trend in the formation constant can also be observed when in copper complexes where Jan-Taylor effects is observed. So remember, what was that? We have found that in case of copper, the two bonds along the z-axis are elongated. They are longer. CuH2O6. It will have two long bonds when we are talking about Cu. Water molecule. So along the x-axis, these are the two long bonds, and rest of it are shorter. So this is the situation. These are the long bonds, two long bonds along the z-axis. Now when you start adding ammonia to it in a stepwise manner, what will happen? Amines so gradually each of this will be replaced. So you will have replacement of when you add ammonia. I'm showing in a different slide. So ammonia is coming in, so each of these water molecules is replaced. One, then you can expect, so each we will, when we add ammonia, gradually all these water molecules are replaced, and as soon as 4 of them are added, in case of, if you are doing the experiment in a aqueous solution, you will find that after 4, there's no the fifth and sixth ammonia is not added. You never have CuNH3 complex not formed in aqueous system. CuNH3 6, so this 6 is never formed in aqueous medium. In water, you will never have formation of this kind, CuNH6. The fifth and sixth water molecules along the z-axis, they are never replaced. in water. Only if you perform this experiment in liquid ammonia, the fifth and sixth water molecules will be replaced. So that is that. So this is the effect of Jahn-Teller, the Jahn-Teller effect, which is seen in this formation constant also. That the fifth bond is going to be weaker. Fifth and sixth are long bonds. So when ammonia replaces it, the metal-amine complex that is formed, Mn bond, that is much weaker in the axial positions and as compared to the one already existing, and so it is not able to replace it in normal circumstances in an aqueous system. Okay, so this kind of thing, when you, so now what we are going to see, the trend of actual values, how it changes suddenly. And so CuNH36 is actually, so this is how you have to see many books mislead you. In these cases you have to be careful. Okay, whenever you are writing CuNH342, don't forget there are two water molecules also. Okay, it is an octahedron, it is a distorted octahedron with two water molecules along the z-axis. Many books do not write that, but this is how you have to understand when we write. Okay, so two water molecules are at a larger distance than the ammonias, so these are along z-axis. So actual formula is CuNH3 4 H2O2. So it is an octahedron with two long bonds of water along the z-axis. So there is a difficulty in putting the fifth and sixth ammonias on the metal, and so bond distance of the two axial position longer than, so this is the trend. So look at the trend here. In water, so imagine you are performing this experiment in aqua system as you do normally. So you start adding ammonia 1, K1, K2, K3, gradually decreasing K4, and you see the values here. All these are greater than 1. Okay, the fifth one is 10 to 3 into 10 to the power minus 1. The K6 is very very small. So 3 into 10 to the power minus 1 means you have, you're talking about a very small value. So the products are less than the reactants at the equilibrium. So when you have K is positive and is having high value, such as here 10 to the power 4, which means that the product, that is the complex, is much more in number. It has greater concentration, 10 to the power 4 times greater concentration at equilibrium when it is compared with the reactant. But in this case, when the number is like this, 10 to the power minus 1, that means the products are very very less as compared to the reactants on this side. Okay, so which essentially means that you will hardly see any formation of NH3 5 in water, and the last one is almost never seen. So fifth and sixth ligand are, so practically what happens, you see only up to this CuNH3 4 with a positive value, high value greater than 1. So number of products is much greater as compared to the reactant side. Okay, and it is abundant. So this is due to the Jahn-Teller distortion that we have seen already. The bonds along the z-axis are elongated, and when you, this elongation has a role to play in the formation constant here that we see as fifth and sixth NS3 is very difficult to put in, and almost practically it is not found when we find this. Okay, so a special case has to be discussed here with respect to the formation. So denticity, so bidentate, monodentate, these are terms that, so that is how many, one molecule have more than one donor atoms, so then we say that they are polydentate. Monodentate is only one. Bidentate means you have right, two tetra, so like that. So you have example, so you have experienced it all in your practical classes. Remember, EDTA, hexadentate, you have done that. Okay, so let's see. So this denticity teeth means so it is, we are visualizing these donor atoms at the uh, what we call as teeth, and that's why the denticity. And also this also later on gives the idea of the bite angle later on. So these are the molecules, monodentate ligands, so all of them um, and thiocyanate, these are ambidentate, you know. So within the monodentate you have another class which is ambidentate, which can at one time it can bind with only one, but either through nitrogen or sulfur. Thiocyanato is sulfato, thiosulfato, like that. So you have nitro, nitrito. This you have prepared these samples for cobalt. Ethylene diamine, En, oxalato, EDTA. EDTA is the thing that you have already done. You have already done that. So oxalate, ethylene diamine, and ethylene diamine. So these are the two donor sites, and three of them can combine in an octahedral fashion. And so this is example of ethylene diamine 3 plus. So this is what we know. So there's unusual thing, these kind of complexes where you have more than one donor sites in one molecule, one ligand molecule, the stability is enhanced. Why is that? We call it chelate complex. Chelate derived from the claw or chela in Greek, from the lobster. So it is like the claws of the ligand can be visualized as a lobster holding the metal ion with its multiple hands, multiple claws. Okay, so this is and so that is produces a heterocyclic rings which ties at both ends with the metal, so that gives a very good stability. So let's take the example here, try to understand more on this. So निकल का एग्जाम्पल है यहाँ पे, निकल अमीन कॉम्प्लेक्स हमने देखा, द ओवरऑल फॉर्मेशन कांस्टेंट इज 8.6. so 6 NH3, 6 water, here it is released. This is the beta is overall formation constant. Overall formation constant is this. Now if you look at the overall formation constant for this NiH26, and here we are adding ethylene diamine. So nature of bond is nickel with N. Here also the bonds formed are same. Look at the individually the bonds. It is still the nickel and nitrogen bond. Nickel with nitrogen. But look at the values here. The overall formation constant is 18.3 log of the, compare the log values, 8.6, 18.3. So about in real terms it has gone up by 10 times, 10 to the power 10, a factor of 10 to the power 10. The formation constant changes by, so that's a huge gain in the stability. So larger the value of overall formation constant, greater is the stability. इसको हम स्टेबिलिटी कांस्टेंट भी कहते हैं कि वो, सो ऐसा क्या हुआ, वो तो नेचर ऑफ एटम्स तो सेम है, निकल के साथ ही नाइट्रोजन का बॉन्ड बन रहा है, लेकिन इसमें इतनी इतनी ज़्यादा वैल्यू क्यों आ रही है? सो लेट्स ट्राई टू अंडरस्टैंड दिस. सो similarly now if you So if you take the first complex, Ni-nickel-amine complex, and add ethylene diamine, it is possible, it is spontaneously you will see that ethylene diamine 3, this complex is formed, and the beta is this. That is, ethylene diamine forms a stronger complex. So if you have ammonia NH3 6 complex and you add ethylene diamine, it is easily replaced. The ammonia is replaced with ethylene diamine with a formation constant of about log of the formation constant, log beta is 9.7. That's also a huge difference. So this difference tells you about what additional thing, ये वाला जो ओवरऑल फॉर्मेशन कांस्टेंट है, ये इन दोनों के बीच का डिफरेंस है। आप देख रहे हैं 10 by a factor of 10 you can see this difference. So the in both cases it is this metal and nitrogen bond, nickel nitrogen bonds are formed in each case, but due to the formation of chelate, the ring that we have seen here, the stability goes up, stability increases by several fold. So why is that is happening? So this, the observation practically when it was observed, it was called Chelate effect, taking resemblance from the lobster holding a small sphere. So chelate means claws, and so metal ion being held in the claws of the ligands having multiple hands. So it is when you look carefully at the reactions, you'll find why it is happening, and it is somehow related to the entropy, because it is not related to the bond strength. The bond strength is same in both the cases, but the overall stability can be accounted for. We can talk about, understand the overall when we overall stability when we understand the entropy part here. So how do you try to understand? Look at the number of molecules, water molecule that you see here. So just let me go back to the slide, previous slide. So how do you account for entropy here? एक minute, just a moment. Let me go back here. Let's see. So see, on the left hand side, one molecule, 6 molecules here. So and right hand side, 1 plus 6 here, 1 plus 6. Now look at the another one. In this case you have 1 on the left hand side plus 3. So you have situation on the reactant side, you have 1 plus 3, and here 1 plus 6. So the reactant and product side is, you can see the difference here. So number of particles, the number of molecules on free molecules which are roaming around randomly moving has increased in this particular reaction when by a factor of 3. So the difference is 3. In this case, the 1 plus 6, 1 plus 6, there is no difference in the number of molecules on the reactant and product side. But here the product side has 7 particles, but the reactant side was having only 4. So that means when 3 ethylene diamine molecules are approach this aqua complex, 6 water molecules are released. So 3 versus 6. So there are 3 new additional species which are being created, which are roaming freely in the solution, which are moving freely in the solution. So so that will cause increase in the randomness, increase in the entropy of the system. Okay, so this comparison, if there is change in the numbers of the free ligands from left to right, then that will cause increase in entropy, and that we see here clearly. And when you calculate the delta G, so this log K uh, K is equal to minus RT ln K. Del G. क्या लिख रहा हूँ? Del G is equal to minus RT ln K. Right, this is what you already know. So K is here. This is the formation constant. So here log K has overall formation constant is can be written as beta. Okay, and so overall formation constant is related to this. So del G. So this thing is also related to the enthalpy, which is the so del G is what? Del G is what? You have del H plus T delta S. So this thing is related to your beta. Okay, and del H enthalpy was related to the bond strength. Del S is related to the randomness in the system, or increase in the number of free species produced. So this second factor, del S factor, is also contributing to this overall formation constant, right? And del S, clearly we can see here that when there is three ethylene diene molecules are there in the reactant as reactant, there are 6 water molecules produced, which will increase the randomness of the system. Okay, as they will keep moving freely in the solution. So that makes it favorable. Okay, so that entropy effect is the main thing that we have. So it is basically the entropy driven process. We say that chelate effect is basically the chelate complexes are formed. They are much stable mainly due to the entropy, or the reaction is driven by entropy. Okay, because there is not much difference in the bond strength. So for example, third one that we had considered, nitrogen bond on the left hand side, reactant side, nickel nitrogen bonds on the right hand side. There is no difference. The sole difference. So this is only due to entropy. This is happening only due to entropy. Entropy driven process. We say that it is entropy is the driving force. Entropy driven process. Okay, there is no difference in the bond strength. So this is one of the things that we have considered. So this is how the thermodynamics explains the formation of strong complexes in this case. So reaction entropy we have seen in dilute solutions. Chelation reaction results in increase in the number of independent molecules in the solution. We have just seen that number of independent molecules in the solution has increased, which roam freely. They contribute to the randomness. Overall entropy increases. In contrast, non-chelating reaction produces no net change. We have seen that when you have NH3 H2O6 replaced by NH3 the same number of molecules remain in the solution. So former has more positive entropy and hence it is more favorable process. The reaction entropy is measured in has been measured in dilute solution, and this so there are experimental evidences that this is happening solely due to the entropy. So this was the thermodynamic consideration explaining the chelate effect. But there is one more aspect that we can relate to. Suppose it is a polydentate ligand has bound to a metal ion. So if you try to break one of these bonds, so it is more likely to recombine with the metal. Agar, where is this structure? So suppose you try to break this bond. It is imagine this is a molecule in a solution. If you try to break this thing, metal nitrogen bond, then because it is still anchored here, still bound to the other thing, it is more likely to recombine with this. In other cases, if it would have been a free ammonia molecule, once it is the metal nitrogen bond is broken, it will swept away. It will keep moving in the other direction, and there's no chances of recombination is there. So kinetic factors also control it. So kinetic, समझ रहे हैं आप? So because they are now still closer, they can still have a, so this is what we have. The kinetic considerations also favor the binding this thing. So thermodynamic plus kinetic factors both control it. मतलब आप इस तरह से समझिए कि एक इमेजिन कीजिए कि मेटल अमोनिया कॉम्प्लेक्स है MnS3, और उसी की जगह इमेजिन कीजिए कि एक मेटल इथाइलिन डायमीन का कॉम्प्लेक्स है, सॉल्यूशन में है। आपने मेटल लिगेंड बॉन्ड को तोड़ा, Mn बॉन्ड को तोड़ा in case of simple metal ammonia complex, then what will happen, that nitrogen will that ammonia molecule, once the bond is broken, it will keep moving away from the metal center. But in case of ethylene diamine, अगर वो आप थोड़ा सा भी एक बॉन्ड को तोड़ते हैं, लेकिन दूसरा वो बह के कहीं दूर नहीं जाएगा, वो it cannot move away because it has the second end, the other end of the molecule is still bound to the metal, and so there is a chance that it will recombine with the metal. तो इसलिए वो स्टेबल ज़्यादा होगा, ये भी एक फैक्टर. So what we have seen is, so consider this reaction. What we have so far learned, that ammonia, when it is added to nickel amine aqua complex, all of them is replaced. So which shows that uh, the K values are much larger. Overall formation constant is positive and has a high value. That means NH3 is a stronger bond, stronger ligand than H2. It forms a stronger bond as compared to H2. Okay, or you can say del naught for NH3 is greater than del H2, or you can also say that it is more stable, and so del G is negative, del S is 0, that we have seen here, number of S3. Del G for the reaction is negative because of the change in the bond, NiO bond to NiN bond. So here NiO bond to NiN bond is the change. So delta H negative, when we are talking about, it is related to the bond strength. There is no change in entropy of the system. Del G is negative. Now, so now we are just trying to finish it. Uh, so what we see here. So now, so this so this is how we interpret the things. Chelate form. When the chelate ring is formed, see here NH36. In this particular case, here also you have Ni nickel nitrogen bond. Here also you have nickel nitrogen bonds. The only difference here is that you are coming out is due to change in increase in the number of 6 and 3. So number of free species, free ligand molecules have increased, and that's why overall there is a change. Del S is positive. In this particular case, del S is positive. Both have similar end donor environment, but because ethylene bidentate a chelating ligand, overall del G is negative, and the major thing is that del S is positive. So reaction proceeds due to the gain in entropy, and this del S is the major factor behind the chelate effect. So if you just try to compare these things, another example of entropy gain, cadmium amine complex. So for amine complex, here also the metal cadmium nitrogen bond. So this is another example where one of the ammonia has been hydrogen in ammonia has been substituted methyl group. This is, and the third one is with respect to this. So what you see here, look at this charge. 4NH3, 4MENH2, 2 ethylene diamine. The values are here with ammonia only. NH3 7.44. This is the overall formation constant. Then when one of the hydrogen is replaced with methyl group, the value decreases. So that is because it creates hindrance. Okay, so in the one, it prevents metal ligand approach because of the steric hindrance, so the values decreases. But when you have ethylene diamine in the case, then the values goes up. So this is the gain of entropy. So compare the del G value, minus 60. So del H, you can see that del H is, the bonds in all of them are same, nearly the same. uh, the bond strength is nearly the same, it is not much affected. But the calculation when it is done for del S, you can see clearly that this has sudden increase. The entropy is the factor here. Entropy is decreasing when you have methyl MENS2. Okay, because the molecule, so a free methyl group was able to rotate, methyl group with the NH2 was able to rotate freely. Now when it is bound to the metal center, it will not be able to rotate, so freedom, randomness decreases, entropy decreases, minus 67. In case of this, when ethylene diamine binds to the thing, you have there's difference, 4NH3 species are released, so 2 versus 4. Overall there's free species increases, so delta S increases by a huge amount. देख रहे हैं? तो जो कीलेट इफेक्ट है मेनली एंट्रोपी का इफेक्ट है, एंट्रोपी इफेक्ट है, ये चीज़ समझने की कोशिश कीजिए, क्योंकि डेल्टा एच फैक्टर जो है वो लगभग सेम है, ऑलमोस्ट द सेम. डेल्टा एच इज ऑलमोस्ट the same. The main difference turns out to be in a chelate thing is that entropy, increase in entropy. Okay, so again and again we can check it with many different examples. Nickel amine complex, delta G, delta S, and the chelate effect. ठीक है, so this is the reaction CuNH3 2NH3, and so you can check here also. Look at the first one, 2 ammonia, beta is 7.7. Look at the second one, when instead of 2 ammonia you have ethylene diamine. In that case delta S is 23. Okay, there's only small so this factor is, so it is increasing by 3 times. there is only a small increase in delta H for the same set of thing. Okay, so these chelating agents are very useful. They strong, very strong complexes, and they can be used for removing unwanted metal ions in water. Selective removal of mercury, lead from body whenever there is poisoning. So these are EDTA and others are used. Preventing blood clots and solubilization of. So there are many applications of these chelating ligands, and some of the examples are like DMPS, effective chelator with two thiol groups, and thiols bind to the mercury very strongly. So mercaptosuccinic acid, pencil. So these are the typical. So in treatment, when you have mercury poisoning anything, these are the things that has been used. EDTA we have already seen. We have done experiments with that. So N as two donor sites and four donor sites for O minus. O minus acts as so lone pairs of nitrogen and the electrons with the O minus. So these are the six donor sites which make up, and this is the structure of cobalt EDTA. Oxygen. This is your oxygen, and this is your nitrogen. Okay, the blue ones are nitrogen, four oxygen. That's making it up. Uh, so this is EDTA forms a very strong complex because all these six donor sites are arranged at the vertices of an octahedron, and so one metal ion is hold up. It is being caught between the hands of six hands of a ligand. Then you also have macrocyclic effect. This is extension of this chelate effect. So this is a particular ring that you can see. Macrocyclic is a ligand of this type. This is a macrocyclic ligand. So here the advantage, they have multiple donor atoms held in a cyclic fashion. Okay, so here when in previous cases you were having formation of ring was happening in all the cases whenever chelate ring was formed, chelate complex was formed. So during the formation of chelate ring there was some strain developed in the molecule, the ligand molecule. So that strain developed in the molecule of the ligand molecule reduced, so that was acting against the stability of the system. But here what happens that the ring is preformed. Prior to the formation of complex, the ring is there. Only the metal ion has to come in and fit into the space. So metal will come and the donation will happen. So this kind of thing. So because of the, so there are two things here. So this is a phthalocyanine ring which you are seeing here. So the additional, so it has all the benefits of a chelate effect that you have seen previously. In addition to that, there is no new ring which is being formed before the reaction and after the reaction. The ring was already there, so there is no additional strain due to the formation of the which was there in the previous case. So it is the pre-organized nature of the ligating group. The ligand is pre-organized, पहले से ही रिंग बना हुआ है, तो रिएक्शन के दौरान कुछ कोई भी स्ट्रेन नहीं आ रहा है, डेवलप नहीं हो रहा है, और इसलिए ये और भी ज़्यादा स्टेबल होता है. सो नो एडिशनल स्ट्रेन इज generated during the coordination of this ligand with the metal, and this is the macrocyclic effect. बाकी सब तो जो पढ़ा था वो आप पहले पढ़ा वो सब ठीक है, उसके अलावा ये एडिशनल फैक्टर है. एंड सो यू विल फाइंड दिस थिंग इन नेचर. क्लोरोफिल का एग्जांपल है फिर बहुत सारे कॉम्प्लेक्सेस बॉडी में होते हैं, सो जिंक का यहाँ पे थैलोसाइनिन के साथ कॉम्प्लेक्स है। सो मैक्रोसाइक्लिक इफेक्ट इज अ combination of entropy effect as in Chelate together with an additional energetic contribution coming from pre-organized nature of the liganding groups. So no additional strains are introduced, and so this is so formation constant of this is likely to be very high, 10 to the power 25. So whenever you achieve if you do perform experiment and the formation constant is found to be that high, you can say that definitely chelate or macrocyclic effect is in the picture. ठीक है? So uh, so that's all for this time. We'll discuss. So आज के लिए बस इतना ही.